The first of our triangle congruence theorems is the median congruence theorem. So what's a median? A median is a line drawn between the midpoint of a side and the vertex of the angle that's opposite. So I've drawn the three medians of an arbitrary triangle ABC. I've drawn the medians in blue. Now, let's talk about what the word concurrent means. Concurrent, a point of concurrency is the point of intersection of three or more lines. So two lines aren't really concurrent, right? I need three. So what we're saying is the medians are concurrent at a point which we're eventually going to call P1. Now, it looks true just because I did it in GeoGebra and it happens to be true. So the relationship, appears to be true, but it's not. Let's talk about what we're assuming here. So we've got an arbitrary triangle ABC, we've got the medians, and we're saying, hey, any two of the three medians will intersect, right? The crossbar theorem says, that they're gonna, these points in the interior, there's gonna have to be a place where they cross. But that's only true for any two of them. What could possibly be going on with this line segment BZ is that it could, I could have this line segment BZ, but this point where they meet, say this is P prime, right? There might be some other point where the segment BZ goes across XZ. That's what we're trying to prove. We're trying to prove that BZ will actually go through this concurrency point P. That's what we want to show. We don't know that. All right, so the next step, we are going to create a bunch of parallel lines. We're going to do this in a very particular way. So if you look at this, we're focusing on lines that are parallel to the median AY, okay? And the idea is that these parallel lines go through all three vertices of the triangle, and then the two midpoints that AY doesn't already go through, right? So AY goes through a midpoint already. It goes through Y. And so we're going to draw a line through these other midpoints, okay? Now, I didn't say it explicitly in the text, but these lines are all parallel to each other, and because they include AY, this set of parallel lines, all of them are parallel to the median AY, the median segment AY. Now, we have this relationship at the bottom of the triangle, which we're going to prove. We need a couple of steps. It's true. Now that we've drawn these parallel lines, we can see it. But let me prove that the segments BD, DY, YE, and EC are in fact equal segments. All right, I need to prove this. So let's clear out our drawing and start. Okay. So first things first, I have a transversal. The side of the triangle AB is a transversal that cuts L1, L2, and L3. And it cuts it in such a way, the way we've drawn it, right? These parallel lines go through the midpoint X of AB, and they go through A and B. So I know that the distance between these parallel lines, like if I draw, the perpendicular, right? I know that these segments up here are congruent. Why? Well, because this segment will be a transversal, and by the lemma, we'll know that these segments are congruent. And then it's also true for this, right? That that I'll have congruent segments here. Why? Because the side of the triangle AC is a transversal that cuts parallel lines L3, L4, and L5. And so is this line that I draw that's perpendicular. And so therefore I know that the distance between the parallel lines L3 and L4 and the distance between L4 and L5, I know that those distances are the same, right? And the distance between a point and a line, if you recall, is where I drop a perpendicular from the point to the line. Well, the distance between two lines is just the perpendicular if they're parallel, right? The only way I could have a distance between two lines is if they're parallel. And then I drop that perpendicular, same thing. So now we know that the distance between L3 and right, but I know the distance between L3 and L4 is equal to the distance between L3 and L5. I also know the distance between L1 and L2 is equal to the distance between L2 and L3. But what I don't know is that the distances over here are equal to the distances over here. That's not clear yet. And I bet you can see why it is. Let me clear out this drawing again. Right, how do I know that if I find the distance between a point on L3 and L5, and if I find the distance between a point on L1 and L3, how do I know that these distances are congruent? These distances are equal. Well, it comes from this side of the triangle BC. And if I take the drawing back one step, you'll see, right, that we have, you can see that that y is a midpoint, right? So I know that by is congruent to cy. So I know this relationship is true by the transversal, so the third application of the transversal congruence theorem, right? So that's what I'm saying down here. You actually have to apply it 3 times. Once for side AB, once for side AC, and once for side BC. So now I know that these links are the same. So if those links are the same, then now I know that all of these segments have the same length. All right, but I have to actually apply the congruence theorem 3 times. And once I do in fact get this relationship that's shown now in the drawing. Okay, why is that important? That's important because we know that P is 2/3 of the distance from C to X. Well, why is that? Well, because CX is a transversal that cuts these parallel lines, and we know that the distance between all of these parallel lines is the same. So I know that the distance between, let's put a point in there, right? I know that this distance is, this segment is congruent to this segment is congruent to this segment. So I have 3 congruent segments, and P is at the endpoint of these 2 segments. So I know that P is 2/3 of the way from C to X. That's going to be important. Let's clear the drawing again. Now, I've done a couple of things. So I'm going to draw parallel lines again in the exact same way as before. So you see the parallel lines M1, M2, M3, M4, and M5. And I also see that I've drawn this orange potential segment, right? So in orange here, I've put the what might be possible, right? What if the median BZ doesn't actually cross through that point P? Right? What if it goes across the line segment CX in some other place, P prime? All right. Well, how do we construct the lines M1, M2, M3, M4, and M5? Well, we've done the same exact thing, except for this time we've focused on the parallel line BZ. Okay, so every single line is going to be drawn parallel to BC, and once again, we're going through each vertex of the triangle. And we are also going through the medians that we don't already have, right? So BZ already goes through the median Z, the midpoint Z. So we're going to make sure that we have lines that go through the other 2 midpoints, X and Y. So that's how we're drawing these lines. And as before, we have these congruent segments that you can see marked here, right? So we're using the double arrows to mark it since this drawing is getting really busy. So we're just using the double arrows there to show the congruencies. And I didn't put in the other points because we don't need it. What we need to understand is that and by the way, we still had to apply the transversal congruence theorem 3 times to get all of that, but I've shown that before. So once we have it, we were like, okay, well now I know that these 4 segments on any transversal between the parallel lines M1 through M5, I know that those segments will be divided into, the transversal between the parallels will be divided into congruent segments, I know that's true of any transversal. And so I'm going to apply that to the transversal CX again. Well, what happens to CX? Well, CX is cut by M4 and M3 and M2 and of course M5, right? So I know that it will divide CX into 3 congruent segments, which implies that P has to be on P, right? If the median BZ intersects CX 2/3 of the way between C and X, well then it intersects it at P because that's where P is located. Well, now we know that the median BZ actually goes through the point P. So now I know that all 3 of the medians are concurrent at this point P. So it's kind of an interesting set of proofs that we went through. We needed this theorem that when I have these equally spaced parallel lines, that it's true for any set of parallel lines, any transversal, right? That's what allows me to get this this 2/3 distance along C to X for P. But I had to apply it twice, right? I create 5 parallel lines through using one median, and then create 5 parallel lines through another median, which proves this relationship along the 3rd median that the concurrency point is 2/3 of the way from C to X. So that's how the proof goes. And we will have multiple concurrence theorems. So it's true that angle bisectors of a triangle are concurrent at a single point. It's true that the perpendicular bisectors of the sides of a triangle are concurrent at a point. And we'll talk about those in a later chapter.